Hi everyone, and welcome to this lesson on binary arithmetic and hexadecimal. This is a key topic in GCSE computer science, and by the end of this video you'll confidently convert between number systems, perform binary calculations, and understand how computers manipulate data. So let's dive in. Here's what we'll cover today: converting between denary, binary, and hexadecimal, like translating between languages, adding 8-bit binary numbers, and spotting overflow errors. So what happens when calculations exceed a computer's limits? And using binary shifts to multiply or divide numbers instantly. So stick around, we'll tackle examples for all of these number systems. Let's warm up with 3 quick questions. So what's the binary equivalent of 7? Convert the binary number 1001 to denary. Add these binary numbers 1001 plus 110. Pause the video if you'd like to try these yourself. Right, so here's how you solve them. 7 in binary is 111. Think of it as 4 plus 2 plus 1. Now the best way to get to this answer is by using the place value system that we discussed in lesson 1 of this unit. If you haven't watched that video, you might want to go back and watch lesson 1 of that video. It's 2.1. Question 2. So 1001 in denary is 9. That's 18, 04s, 02s, and one lot of 1. Adding 1001, which would be 9, and 110, which would be 6, will give us 1111 in binary and 15 in denary. Now remember, binary addition works like denary, but you only use zeros and ones. Let's practice converting 8-bit binary numbers. Imagine a table with place values. So starting from the left and working to the right. 128, 64, 32, 16, 8, 4, 2, and 1. So for example, 0101, 1001 has a 1, the number 1, under 64, 18, 8, and 1. You would add them up, so 64 plus 16 plus 8 plus 1 would give us 89. Now, you might want to have a go at this yourself, again, if you have not watched the first video of this unit. Create the place values on a table from 128 all the way down to 1, and place the binary digits 0101, 1001 according to how we've explained it just here, and then you'd be able to see the conversion for yourself. So here's a quick tip as well. The last bit tells you if a number is odd. So if a number is odd, it ends with 1. Or if it's even, it would end with 0. Use a place value system again and try converting 1100, 0010 yourself. So here's the simple rule to converting binary to denary. So you will start with the largest power of 2, less than the number that you're trying to convert, and then subtract it and write 1 in that position and 0 everywhere else. Let's have a look at some of the solutions to the examples that we've looked at as well. So denary number 14 is 1110. Sorry, my bad. Denary 14 is 1110 in binary. Denary 105 is 1101001. Do you notice how the last bit matches odd even? So 105 is odd, so it ends with a 1. Hexadecimal, or hex, is base 16. It uses 0 to 9 and A and F, where A equals 10, B equals 11, up to F equals 15. For example, F in denary is 15. 10 in hex is 16 in denary. So just to reiterate that, F in denary is 15. 10 in hex is 16 in denary. Hex is like a shortcut for binary. It's more compact and easier to read. To convert hex to denary, multiply the left digit by 16 and add the right digit. For 2a, we would do 2 times 16, which would equal 32. A would equal 10. So the total would be 32 plus 10, which would give us 42. Now try 27 in hex. 2 times 16 plus 7 would give us 39. Using a hex place value table, as you can see on your screen, is always quite useful to carry out these conversions. In an exam or when you're answering a question, you may be given this table. If not, it's pretty straightforward to kind of draw out and use yourself. Next, let's look at denary to hex conversion. To convert denary to hex, divide by 16. The quotient is the left hex digit. The remainder is the right digit. So for example, denary 18 would be 18 divided by 16, which would equal 1 remainder 2. So 16 would go into 18 once with a remainder of 2. The hex would be 1, 2. So we don't say 12, we'd say 1, 2. So the 1 we get because 16 goes into 18 once, so we have 1, and then we have the remainder, which is 2. So we say 1, 2. Now convert 27. So 27 divided by 16 equals 1, and the remainder is 11. 11 in hex, using the place value table for hex, we can see is B. So again, 16 goes into 27 once, so we have a 1, and we have a remainder of 11. 11 in hex is B, so we would have 1B. For 44, if we look at another example, for 44, we would have 2 times 16 plus 12, which would be C. So 12 is C in hex. So we can see that 16 will go into 44 twice, so that's why we have a 2. And we have a remainder of 12, and 12 in hex is C. So when we put those or combine those together, the answer is 2C. So let's recap. Hex 27 equals 2 times 16 plus 7, which would be 39 in denary. Denary 27 would equals 1B in hex, denary 44 would equals 2c in hex. So hex or hexadecimal is all about breaking numbers into 16s and units, just like denary uses tens and units. Here's a trick to convert binary to hex. Split the 8-bit binary into two 4-bit nibbles. For example, 11100101 would end up being 1110 and 0101. Convert each nibble to hex. So 1110 would equal 14. 14 in hex is the letter E. 0101 would equal 5. And 5 in hex is 5. So 1110 0101 in binary would be E5 in hexadecimal. This works because 4 bits map perfectly to one hex digit. Let's reverse it now. So convert hex 3b to binary. 3 equals 0011 in binary, and b equals 11 in binary, which is 1011. Now when you combine them, you will get an answer in binary 0011 1011. Now try A5. So A equals 1010, 5 equals 0101, and combined they would give us a binary digits of 1010 0101. Hex to binary is just expanding each hex digit into 4 bits. So why do programmers prefer hex over binary? Well, it's shorter. So compare E5 to something like 11100101. There are fewer errors. So typing A3 is safer than writing the binary equivalent, which is 10100011. It includes easy conversion. So hex and binary are kind of like best friends. Each hex digit maps into 4 bits. It's like using abbreviations for long words. Binary addition follows 5 simple rules. So 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. Now when you add 1 plus 1, you would actually put down 0, but you would carry 1 over onto the next on the next column. 1 plus 1 plus 1, you would actually put 1, but you would still carry 1 over to the next column. So let's have a go. Let's add 1010 and 0111. So start from right, carry over ones, and combine. You should end up with 10001, which will give us 17. Now the easiest way again to add these up is to use the place value table to help you do this. It's very straightforward. Computers have limits. If you add two 8-bit numbers and the result needs a 9th bit, you get what we call an overflow error. For example, 1111000 would equal to 240 in denary. And if we tried adding 1001111, which is 159, if we tried adding these values together, that might cause a problem because we would end up with the answer 399. But an 8-bit system can't store the 9th bit, so it chops it off, giving a wrong answer. Overflow is like trying to pour a liter of water into a half-liter bottle. Binary shifts are like moving digits left or right. Left shift moves bits left and adds zeros. It doubles the number. For example, 0110 is 6, but if we shifted this to the left, we will then get the number 12. If we performed a right shift, this would move the bits to the right, and it halves or rounds down the value. For example, 1001, which is originally 9, if we shift 1 to the right, we will get 0100, which will be 4 in binary. So it halves it and then rounds it down. Shifts are how computers quickly multiply and divide by 2. So when we look at shifts as multiplication and division, so each shift will double the number. Each left shift, will double the number. Each right shift halves the number. But one thing to be cautious about, right shifting can remove ones permanently, and you may lose precision in the number that you're trying to represent. So why not have a go at trying to test yourself with converting some of the examples, the questions that we can see on the screen right now. It might be an idea to pause the video and have a go at converting these values to test yourself how much you've actually picked up. Consider using the place value or the relevant place value tables for binary and hex to help you do this. And here's the breakdown. C equals 12, 2b equals 0010, 1011. Got question 3, question 4. How many did you get correct? Maybe comment in the comment section below. Let me know how you got on, or if there's anything else that you need help with.